Today, I'm diving into the science behind phasors, force fields, teleportation, and time travel. Let's see how these could transition from fiction to reality. First up, phasors. These iconic weapons from Star Trek can stun or disintegrate targets. Sounds far-fetched? Well, they're actually linked to directed energy weapons, or DEWs. Think lasers, microwaves, or particle beams. The US Navy's laser weapons system, or LAWS, can already disable drones and small boats with high-energy laser beams. And high-power microwave weapons, they can disrupt electronics and incapacitate personnel. To make sci-fi phasors a reality, we need huge advances in energy storage, beam focusing, and miniaturization. Plus, they need to be safe to use without collateral damage. Next, let's talk force fields. In sci-fi, they're invisible barriers that protect against attacks. The real-world equivalent lies in electromagnetic fields and plasma physics. Magnetic shielding already protects spacecraft from cosmic radiation, and plasma windows made of ionized gas can block certain radiation while staying transparent, creating a stable, self-sustaining force field that repels physical objects and energy attacks. That's a colossal challenge. Advances in materials science and quantum field theory could be the key. Now, teleportation. Moving people or objects instantaneously, like in Star Trek. Quantum teleportation doesn't move matter, but it transfers quantum information between particles. Quantum entanglement experiments have shown this over significant distances. Scientists have even teleported quantum states of photons and atoms in labs. The big hurdle? Scaling this up to macroscopic objects or humans. It involves maintaining quantum coherence and dealing with vast amounts of information. Quantum computing and information theory advances might make it possible. Finally, time travel. Whether it's H.G. Wells' The Time Machine or Back to the Future, the idea of moving through time is fascinating. Time travel theories often stem from general relativity, which links space and time with gravity and velocity. Near massive objects or at high speeds, time dilation occurs, effectively letting us travel into the future. Wormholes, hypothetical constructs, might connect different points in space-time, offering shortcuts. But traveling to the past? That's speculative and loaded with paradoxes, like the grandfather paradox. We'd need breakthroughs in quantum gravity and exotic matter to stabilize wormholes for safe travel. Now that we've explored the fascinating realm of sci-fi tech, let's dive deeper into one of the most mind-bending concepts, teleportation. While teleporting humans remains a distant dream, quantum teleportation offers a tantalizing glimpse into the future of instantaneous travel. Teleportation, often depicted as the instantaneous transfer of objects or individuals from one location to another, is a staple in science fiction. But what if I told you there's a scientific basis for teleportation? Enter a real phenomenon grounded in quantum mechanics. Quantum teleportation relies on two key principles. It allows the transfer of quantum information, like the state of a particle, from one location to another without physically moving the particle itself. First, let's break down these concepts. Quantum entanglement occurs when two particles become intertwined, so the state of one particle instantaneously affects the state of the other, no matter how far apart they are. Einstein famously called this spooky action at a distance. Next, the quantum state describes a particle's properties such as spin, position, and momentum. In quantum teleportation, the aim is to transmit this quantum state from one particle to another. The no-cloning theorem, on the other hand, states that it's impossible to create an exact copy of an unknown quantum state. This ensures that teleportation involves transferring the state, not duplicating it. So, how does quantum teleportation work? The process typically involves three steps. Two particles, A and B, are entangled. Particle A stays with the sender, Alice, while particle B is sent to the receiver, Bob. Alice has a third particle, C, whose state she wants to teleport to Bob. She performs a joint measurement on particles A and C, producing two classical bits of information. Alice sends these two bits to Bob through a classical channel. Using this information, Bob performs a corresponding operation on particle B, transforming it into the state of particle C. This process successfully teleports the quantum state of particle C to particle B, destroying the original state in the process. Importantly, this doesn't violate the no-cloning theorem. Quantum teleportation has been experimentally demonstrated with various particles, including photons, atoms, and ions. Notable achievements include teleporting the quantum state of photons over several kilometers and teleporting quantum states between atoms in controlled environments. However, scaling up quantum teleportation to macroscopic objects or humans presents enormous challenges. It would require significant advancements in quantum computing, quantum error correction, and quantum communication. The energy requirements and the volume of information needed to describe a macroscopic object at the quantum level are staggering, posing significant technological hurdles. While we're far from teleporting humans, the breakthroughs in quantum teleportation pave the way for future quantum communication systems and networks. The future of teleportation is a thrilling frontier, blending science fiction with scientific reality. Now that we've explored the concept of teleportation, let's shift our focus to another captivating idea that has fascinated humanity for generations: time travel. A staple of science fiction, time travel tantalizes us with the possibility of journeying to the past or future. While many time travel scenarios remain speculative, modern physics offers intriguing frameworks and theories that hint at its potential feasibility. Time travel in general relativity. Einstein's theory of general relativity provides a profound understanding of how space and time, or space-time, are interconnected and how they can be warped by gravity. This theory lays the groundwork for several time travel concepts. 1. Time dilation. According to special relativity, time slows down for objects moving at speeds close to the speed of light. This phenomenon, known as time dilation, means that a fast-moving astronaut would age more slowly compared to someone on Earth. This effect has been experimentally confirmed with high-speed particles and precise atomic clocks. In general relativity, time also runs slower in stronger gravitational fields. This effect is observed near massive objects like black holes. Thus, theoretically, if one were to orbit a black hole closely without falling in, less time would pass for them compared to someone far away from the black hole. 2. Wormholes. Wormholes are hypothetical bridges connecting distant points in space-time. They arise as solutions to the equations of general relativity. If traversable, a wormhole could allow for instantaneous travel between 2 points, potentially enabling time travel if the two ends of the wormhole are at different times. However, stabilizing a wormhole requires exotic matter with negative energy density to keep it open, something not yet found in nature. The stability and traversability of wormholes remain purely theoretical and highly speculative. 1. Closed time-like curves, CTCs. Certain solutions to the equations of general relativity include closed time-like curves, which loop back on themselves. An object traveling along a CTC could theoretically return to its own past. However, time travel to the past introduces paradoxes like the grandfather paradox, where a time traveler could potentially prevent their own existence. Resolving these paradoxes is a significant challenge for physicists and philosophers alike. Quantum mechanics and time travel. Quantum mechanics, the science of the very small, offers additional insights into the nature of time and its potential manipulation. 1. Quantum entanglement. Quantum entanglement suggests that particles can be instantaneously connected regardless of distance, leading some to speculate about its implications for time and causality. However, entanglement does not allow for faster-than-light communication or time travel as understood in traditional science fiction. 2. Quantum gravity, a theory of quantum gravity, which seeks to unify general relativity and quantum mechanics, might provide new insights into the nature of time and space-time. However, such a theory remains incomplete and its implications for time travel are speculative. 3. Quantum computers. Quantum computers, with their ability to process vast amounts of information simultaneously, might one day simulate quantum systems and potentially model time travel scenarios. This remains an area of active research and speculation. Experimental evidence and practical considerations. 1. Practical time dilation. Time dilation effects are corrected for in the Global Positioning System, GPS satellites, which experience both special and general relativistic time dilation due to their high speeds and varying distances from Earth's gravitational field. 2. Particle accelerators. In particle accelerators, particles reach speeds close to the speed of light, and their lifetimes are observed to be significantly longer due to time dilation. Challenges and future directions. 1. Energy requirements. The energy required to warp space-time sufficiently for time travel such as creating and stabilizing a wormhole, is far beyond current technological capabilities. 2. Paradoxes and consistency. Any theory of time travel must address logical paradoxes, such as the grandfather paradox. Some theoretical solutions propose parallel universes or self-consistent timelines where paradoxes are avoided. 3. Technological barriers. Developing technology to manipulate space-time on scales necessary for time travel would require breakthroughs in materials science, quantum computing, and a deeper understanding of fundamental physics.